All right, guys, in this rapid review video, it might not be as rapid as you'd like because we're going to go through a lot here. So it might be a little bit longer, but play it at 2 times speed and make it a rapid review video. All right, so we're looking at mass spectroscopy versus PES, photo electron spectroscopy. And just really, you're going to have to interpret the 2 different charts. So understand what mass spec charts tell you. They tell us about the different masses of isotopes, so the different mass numbers for the isotopes, their percent abundance, how abundant they are, and the data can be used to calculate the average atomic mass, or maybe predict or estimate what the average atomic mass is. So it's about the mass of the nucleus of the different isotopes of the same element. Remember, PES is just about the electrons and what sublevels they are. Okay, so a mass spec diagram, you can talk about the mass of different isotopes, but you're really not talking about the number of electrons and that kind of thing. In PES, we're talking about the electron configuration. If you're given a full PES, you can identify the element, or sometimes you'll be given partial PES where you're just comparing 2 different peaks of different elements. And remember, it's about binding energy. The x-axis is how attracted are the electrons to the nucleus. So the closer electrons obviously have a higher binding energy. The more valence electrons, the electrons that are furthest away in the higher sublevels have lower binding energy. That's what the x-axis tells us in a PES diagram. And the y-axis is just how many electrons are in that peak. And remember, PES, if you get the full spectrum, you can just identify the element based on its electron configuration. You can say the first peak is 1s2, the second peak is 2s2, and so on. But don't mix and match, right? So PES is about the electrons and how attracted they are to the nucleus. Mass spec is about the different isotopes that element has and what their masses are. So remember, mass is just about protons and neutrons. Okay, so let's focus on mass spec first. So here's a mass spec readout. Okay, so this has nothing to do with electrons, but it says whatever this element has, it has an isotope that weighs 90, an isotope that weighs 92, an isotope that weighs 94, and an isotope that has a mass number of 96. And that total right there would be the protons plus the neutrons. Okay, since they're isotopes of the same element, they would all have the same number of protons. So what's the difference is their number of neutrons. And remember, the average atomic mass is a weighted average based on relative abundance. So since the majority of the the majority of the isotopes are the 90, the 91, and the 92 isotopes, the average atomic mass is going to be closer to this mass and further away from that mass. So from this information, we can glean that the average atomic mass is about this, okay? Again, it'll tell us nothing about what types of oxidation states it'll have. It won't, right? Oxidation state might be like how many valence electrons it has, so how many electrons will it lose, but that's not what mass spec tells us, okay? So here we have another mass spec readout, and this question's a weird one, so pause it and read it to really understand what's going on here. But notice they say all the statements below here are true, so all of these statements are true, and they're asking which one of these statements would tell you that this readout is actually not a mixture of beryllium and iodine, it's just pure beryllium. And part C says, or answer C says, iodine consists of only one naturally occurring isotope with 74 neutrons. Well, if that's the case, then it's one naturally occurring isotope, since iodine has 53 protons, would be 127. And since we didn't get a peak at 127, that means there must be no iodine in this sample, and it's only beryllium, okay? Here we have another mass spec. So this is for silicon, and notice silicon has 3 isotopes, but the most abundant one is 28. And if you looked at its average atomic mass, the average atomic mass is very close to 28. And the question is how many protons and how many neutrons are in its most abundant isotope. So you would say the most abundant one is 28. You go to its periodic table, its atomic number is 14, so 28 minus 14, that means 14 protons and 14 neutrons, okay? Then it also says write the ground state electron configuration. So this has really nothing to do with this readout, but since we've identified it as silicon, hopefully we know how to write electron configurations. If we don't, make sure you go back and brush up on that, all right? All right, so that was kind of like the way mass spec will show up on the AP exam. So let's look at PES. Okay, so remember, in PES, you're comparing partial readouts where you're comparing two different peaks for two different elements. And really, the higher the binding energy would either mean that peak is maybe an energy level 1 peak versus an energy level 2 peak, or if they're both the same energy level and maybe they're both core electrons, then it would just be more protons in the nucleus, or a greater nuclear charge would mean a greater attraction, so a higher binding energy. Okay, and then remember, and here's the deal. I've never seen a partial PES on a free response question. I've only seen partial PESs on multiple choices, and I've never seen a full PES on multiple choice. I've only seen full PES on free response. Now, that doesn't mean they might switch it, but usually if it's a full PES readout, it's going to be on the free response, and if it's a partial, it's going to be on the multiple choice. But that doesn't really mean much, but just get used to how to see it. And then just remember, PES is it ties in with ionization energy. The higher the binding energy, the more difficult it is to remove the electron from the atom, and that would be what ionization energy kind of is. How much energy is required to remove the electron from the atom. Okay, so here we have partial PES. We have two peaks. It's saying one of these peaks is calcium 2+, and the other is argon. And notice normally PES does go left to right, meaning higher binding energy here, lower binding energy here. So that would mean either closer to the nucleus because you have higher binding energy, or more protons because you have higher binding energy. So which of these peaks is calcium and which of these peaks is argon? And so the question is just asking, what does peak X represent? And it would be the calcium peak, because calcium has 2 more protons than argon. So be careful. You probably know it's calcium, and you know it's about its nucleus, but it's not because of its nuclear mass, it's because of its nuclear charge. It has 2 more protons. So a lot of students might not read the full question and pick part C accidentally, because a lot of times they'll say nuclear charge. It has a greater nuclear charge. And if they had said greater nuclear charge here in part C, that would be the right answer. But they didn't say that. They said greater nuclear mass. And the way they said greater nuclear charge, they just worded it a little bit differently here for part D. So watch out for that. Okay. Here's another partial. It's a 1s peak for, there's one of these peaks is carbon, and one of these peaks is fluorine. They're both 1s, so they're both core electrons. They're not valence electrons. And fluorine just has more protons. So since fluorine has more protons, I'm guessing this is the peak for fluorine, and this is the peak for carbon, because the peak for fluorine should have stronger binding energy. Okay, and let's see if I'm right. Yeah, peak X is the fluorine because it's greater nuclear charge. Be careful though. Understand that that's not the reason for peak X to be fluorine. So the answer here is B. Okay. All right. So again, and it's based on the protons in the nucleus. Carbon has a +6 nucleus. Fluorine has a +9. Okay. So here we're given the peak for nitrogen's 1s peak and oxygen's 1s peak. Now remember, nitrogen and oxygen do have an exception to the rule when it comes to first ionization energy, but first ionization energy would be how much energy is required to remove a valence electron. These are peaks of core electrons, so we're not looking for ionization energy exceptions here. This is just oxygen has 1 more proton in the nucleus. So nitrogen atoms have a smaller nuclear charge, or oxygen atoms have a greater nuclear charge, either way. So that's the answer for part D there. Okay. Here we get a full readout. If we wanted to identify it, we could start, again, this is higher binding energy, lower, so this would be 1s2, 2s2, and then 1, 2, 3, 4, 5, so 2p5. So this, if we wanted to identify the element, we would say fluorine, okay? But this leads into questions about light, so make sure you go back and review your light equations and that kind of thing. E equals h nu, C equals lambda nu. They're given to you on your formula sheet. Just understand that the energy that you plug into this equation has to be in joules, not kilojoules, so be careful with that, because Planck's constant is joules times seconds, not kilojoules times seconds, so be careful with that. But the answer for BI, what subshell from which the subshell from which an electron is removed in the second ionization. So the second electron removed would still be from this peak. So it'd be the 2p peak. And the subshell that corresponds to the second peak of the photoelectron spectrum. So that second peak is the 2s peak. All right. So the answer to BI here is the 2p, and BII is the 2s. All right. So here we go again. We'll go 1s2, 2s2, 2p3. So if we needed to identify it, it would be nitrogen. So that's what it said here. Identify the element. And then it goes into radioactive decay and talks about half-life. So that, remember, we just learned about that. First order kinetics, you can use the shortcut. You can use the T1 half equals 0.693 over K equation here. You have the half-life. You can solve for K that way. But just, annotating the PES 1s2, 2s2, 2p3. And then based on the fact that it ends in 2p3, we know that's nitrogen. Okay, all that good stuff. All right. Here, if we wanted to identify it, 1s2, 2s2, 2p6. Now we know this is 2p6. Yeah, we can do the math here, but if you get another peak, then this has to be full, and it's full with a p sublevel is full with p6. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So this would be calcium. We could write the configuration. We could do the shorthand because it didn't say full configuration. So we could say argon in brackets and then say 4s2 if we wanted to. But we got the electron configuration. We identified the element. And then here, notice this said binding energy. A lot of times it's energy per mole of electrons, but this is per electron. So this right here, that would be the ionization energy to remove one electron. So we could plug this energy into our energy equation, solve for the frequency, and then once we have the frequency, solve for the wavelength. Or we could remember our shortcut, E equals hc over lambda, so that means lambda equals hc over E. So this would be the energy value to plug in for E, and you could solve for the wavelength that way. Okay. Here we got another one. Now, this says it's for silicon, and we're missing a peak. So it says draw the missing peak. So remember, silicon ends in 3s2, 3p3. So if we wanted to draw that missing peak, 3p2. So it would just be a little bit higher, or weaker in binding energy than the 3s2 peak, but it would be the same height as the 3s2 peak because it's 3p2. If it was 3p3, then we would draw it up to here, right? If it was 3p4, 3p5, 3p6. Okay, so that was just drawing in the missing peak. Yeah, okay. So that was just a quick review, not as rapid as the other rapid review videos. I apologize for that, but if you listen to it at half speed, it's still, 7 minutes. So, or 2 times speed, 7 minutes, you're good to go. Do the assessment and get your credit for your rapid review assessment of the day, and keep on reviewing. Let's get that 5.